Recording. So welcome. My name's Matthew Gardiner and I'm an artist, a researcher and an Oriboticist. And let's make sure that's working. And so the word Oriboticist goes back a little bit. So the word oru is the Japanese verb for fold, and that's what we hear in origami. So ori means to fold. A bot is the short word for robot. I joined them together in 2004, some time ago now, and came up with the word Oribot. And so it's Oribotics is the research field, and someone who does Oribotics is an Oriboticist. Okay? All right, so what we're talking about today, what I'm introducing today, it's on my t-shirt, is Oribokit. So that's the same idea, ori, bow and a kit. So the idea that you put all these things together for a kit. And, it's in edit mode, great. So I've got sort of a few things that I'm going to discuss, and Oribotics covers quite a lot of fields. It covers the art and design, material research and computational origami. So in the art and design there's Oribotic works, and so they're works that I've been making for some time. So this is a short video of those, and I'm having fun. Great. And it's a lot of fun at the moment. Okay, so this is these works have been produced for quite some time. So Robotics Laboratory is the same flower that appears in the kits. So it's the same design that's been used in all the kits. This work here, Oribotics, The Future Unfolds, was a work that was made in 2010 at the Ars Electronica Future Lab. It's a very beautiful work, very complex. There's a lot of 3D printing to make this work. I think I employed the 3D printer for 1,800 hours in the Ars Electronica Centre. So I just had this machine running constantly in 2010, so I did a lot of work. And this is the work that, so the kit came out of creating a work for a museum in Mexico, for the Centre of Science in Mexico. And so this work was called Oribotics Klima, and it was connected to a weather system. So very similar to Robotics Laboratory. I'm having trouble. I'm just going to change something here. Great. Okay, so I'll just go back a slide. Oh, I see what happened. Okay, I'm actually going to go back quite a few steps. So, the Oribokit is an integrated STEAM kit. It features Oribotics, origami and robotics. So as I started to discuss, Oribotics is my research into art and nature. Origami is the study of maths, geometry and science. And robotics is the code, technology and digital fabrication aspects of it. So we just looked at the Oribotics nature, the Oribotics aspect, and now I'm going to talk about the material research. So I have funded research based in Austria. This allows me to do quite a lot of different things, and one of the things that I've been able to do with this field is do something called fold printing. So fold printing is something that lets me take a 3D printer and print onto textiles. And this is really quite exciting because what it allows is it allows you to take a sheet of textile, take a standard 3D printer and adjust it so that you can print just on top of the textile. And the advantage of that is you can produce really quite crazy origami and so this is an example which sort of ties into this. So what we did during the research is we built this very large scale 3D printer that allows us to do really quite complex origami. And the other example is something like this. So this is a fold mapped origami form. It takes a little bit of an art to put it on, but it's a stole. Don't as a stole, but you've got to adjust it perfectly. But what fold printing allows you to do is do very, very rapid folding. And so this is a demonstration of folding a very quite irregular origami geometry very, very quickly. So what happens is that the folds are instant. They're built into the material after this process. So it's really, really quite fascinating. So the principle is, for folding, what we discovered from this is if you have a more rigid surface on a flexible surface, you've got instant folding patterns. So if, you take any textiles, put any rigid panel on them, so you could do laser cut plywood and stick it onto whatever type of textile and get the same type of effect. The next stage in the research was we looked at a field of computational origami. Well, we developed a field of computational origami that we called fold mapping. And the idea of fold mapping is that you can take a shape, so in this case it's this grey shape on the model, and create a surface, and then take an origami pattern and map it to the surface. Okay, so that also leads to geometries like this, which is a work called the folded geometry of the universe. It's a nautilus-shaped geometry with folds mapped onto it, and that sculpture there is 3D printed. And so what you can see in this graphic here is we've been able to apply all different types of folding patterns to the same geometry and get different results. The result I chose was the lowest resolution, the top middle one here, for making this very strange and very fun hat, which you see me wearing with the printer here. So this was produced in 2016, so it's going back some time, and was the main topic of one of the main topics of my PhD research. And so then this is the folded geometry of the universe. It's this was really a kind of you can have a look, a really kind of beautiful artistic discovery. So I've always been interested in nautilus shells. I've always been interested in looking at nature, and when I applied the fold mapping technique, because I was still writing the software to do the fold mapping, and this was one of the first kind of discoveries, and it was quite amazing to find it. I really like the sculpture from the point of view that it represents an infinite shape. So spirals can go infinitely large and infinitely small. And this is very similar to origami itself. We can find folds at the universal scale in the pleated shape of dark matter. And we also find it in our muscles as proteins fold and unfold. This is quite a beautiful area. So the underlying science of origami is actually in the folding patterns. So this might sound strange, but the folding patterns themselves are a subject of scientific discovery. So the first pattern, which I really, really love this pattern, is called the Kresling pattern. It looks like this when it moves. The scientific discovery is that if you take a cylinder and you twist it, what happens, or if you hold two parts of the cylinder and you twist it, the cylinder forms this, what it does is it buckles in this shape, and it's completely reliable. The beautiful thing, there is one of the Oribots here has a Kresling pattern embedded in it. It's really quite fantastic because it can extend and contract, and if you have two opposed layers in it, what happens is it expands and contracts without any rotation. So the two, because they work in opposition to each other, the two segments. The other thing you can do is if you have them all going in the one direction, as you compress it, and decompress it, it rotates. So both ends of it rotate. So it's actually quite a programmable mechanical object. It's very beautiful. The fellow I was talking about earlier, Koryo Miura, professor, he found this folding pattern called the Miura Ori in in the study of, he found it by simulation, which I really find quite amazing. Back in the 70s, they were using a lot of repeated calculations to see what would happen to shapes under pressure. And one of the ones that they found was the Miura Ori. And what's really beautiful about the Miura Ori is it's planar. So it's about compressing a sheet in two directions together. And as it compresses, so what it does is it keeps the same height, or it changes in height, but the whole surface stays one height. It's also a mechanism that has 1 degree of freedom. So that means if you make this out of steel, hinged steel, and you move one part, the whole sheet has to follow suit. So you can do really quite incredible mechanical things with the Miura Ori. It's one of the most studied ones. Going back a little bit further is the Yoshimura pattern. And this one's great because I really like the story of how this was discovered. It was discovered by looking at aircraft wings, which of course have a little bit of a curve in them. And so in collisions and crashes, what was happening is they were starting to see a certain pattern emerge. And it's basically the result of the pattern. If you compress a cylinder, this is what happens to the surface. It does this very, very quite beautiful geometry. It's similar in way to the Kresling pattern, but what it does is it doesn't stay in a cylinder. So it's more like if you wanted to have a mechanism that went from flat to curved and back again, the Yoshimura is what you would use. The Yoshimura pattern, this geometry here is a fold mapped Yoshimura pattern. So what happens is when we curl it, so when we put the cylinder back into the surface, the folds spontaneously form and they go into their geometry. So it's actually not only works with cylinders, you can also use it with quite other, quite varied geometries. And the last one is the flasher. And so the flasher was developed by Chris Palmer and Jeremy Schaefer again. And they made it as a party trick, as something you can have wrapped up in a very small sort of cylinder and pull it apart and it will expand and contract. And so it looks like this. So it has a rotational folding action. And you can actually do this just if you took like a sheet of silk and you put a cup with some glue on the bottom and you twist it. What happens is you see this pattern forming. That pattern is the same geometry. So what's similar about all of these patterns is they spontaneously occur if you do certain things to certain shapes. I personally found this fascinating to sort of uncover this sequence of ideas. So that's the science behind Oribotics and origami. So that's where most of the research goes in. If you look at all the papers, they're all about what angles can we use in this folding pattern, what are its limits, how can we check if it's rigid or not. So a lot of the questions are very mathematical. So, and it's almost, you actually can't do any origami without doing maths. As soon as you fold a sheet in half, you're making a division. If you fold it in half diagonally, you've made a root 2 division. It's very, very, very beautiful. So the other part of, the next part of Oribotics and Oribokit is robotics. So this is just a little bit of information about the background for this kit. So we use open source code. We run on an Arduino platform. I'm not sure if that means anything to any of you. Yeah, so Arduino was developed as an open source piece of hardware, and to go with that, they wrote software. And that software lets you write a program to the microcontroller to talk to sensors, to motors, and other things like that. So the other part of this is the electronics, which is the electronic design that we've been doing. You can have a look at that. That's one of the boards. And the last part is the digital fabrication that we use. So in terms of STEM education, this covers so many of the bases already. You've got an example of a tool that you can write and update using open source software. You've got an electronic basis which has integrated servos, it has sensors built into it, and the last part is that all of the parts are made through digital fabrication. So I've got a little workshop in the neighbourhood here. It's got a 3D printer, a laser cutter, a 1960s lathe, which I don't use so much for this, but I used to use it for the original kits, and all of that's done. Most schools now these days have got fab labs with that type of equipment, so extensions to this kit, which is what I imagine the kit could ultimately be used for, is first of all you build the basic robot that comes with it, but the interesting part happens when the kids start thinking about what could they do for themselves, or and that's exactly what I love about it. So to back up Oribokit, we've got everything on a GitHub repository. I'm not sure if that means anything to any of you, but it means that you can download the code. Sorry, it's very, very dark here. So we've got setup instructions on there, you know, how to plug it into your computer. We've got an example code that we use. It's the GitHub link if you like, but that's also on the Oribokit website. And the next part is the electronics, which is, this was the original board. You can have a look at that one. So they got the 3D printed parts. That was when the production house I use in China only did green. Now I like black. So I do everything in black now. And what we do on the website is we provide all the documentation that you need. So this is version 1.5. It details all of the connectors that are on the board. This stuff is on the GitHub repository. So if you're adapting this to your own purposes, you know, if you want to write your own Arduino code, you look up here and you go, okay, analog pin 3, it's called A3. Everything's labelled as it would be to use in Arduino. So it's not meant to be super complicated to use. As you can see with these ones here, they've got RGB LEDs built into them. These are the new generation of bots. I've got a design patent in at the moment. It'll be a couple of months before that's accepted and resolved. And so from June onwards, we've got a very exciting new board which comes with the LEDs. The design you've got in front of you, if you guys didn't grab one, I can grab one. Is the same one as this one here, but just a little bit simplified. And it's very beautiful. So the other thing that it's involved here is the digital fabrication, and this is a little video showing all the different parts. But inside the kit, all the paper is pre-laser cut, as you can see on this example. The folds are perforated, so if you want to, as you fold, they fold really nicely and easily. You don't have to think about where to fold. And it's all set up. So, you know, the quality of the parts has kept jumping. Now I use a resin printing process, so they've got very high resolution parts that I used to have to go down to Bunnings, buy, cut, machine. I now just print. You know, and it's fantastic, the quality of that you can get out of that. So now this is about your mechanism. You don't have to do it now, but I wanted to make sure everyone had one. It's a mechanism that's this one here, and and if you want to make them, I've got a little video here that sort of goes through the process. It'll run through again, but basically I didn't want to keep you for super long time, but I'll just leave this running for the time being now, so you can have a go at building it. I'm going to plug this one in, and basically you can it's very, very free now. Here we go. So the difference between this mech and the other, and there's also little folded instructions on the side, so you get an idea of how it goes together. The difference between this mech and the the blossom here is that there's two different materials. This is a single material type. And also what you'll notice is the difference, another difference is that the mechanism actually comes alive when you hook it up to the Oribokit. Okay, so this as it is, you can activate it with your fingers, but once you hook it up to the kit, you can actually get this really beautiful full range of movement out of it, which is very lovely. So this is kind of the introductory idea behind the kit. Yeah, if you've got any questions, it's kind of, we're in open space at the moment. I wanted to keep what I had short and punchy and full of information. Oh, so the other thing that I do is I provide video instructions. I might step out of the way, maybe I'm in the way. And for those of you that are origami purists, I'm sorry, that Oribokit uses a bit of glue. But you'll notice that in part of the kit assembly there is some layering up of paper. This is to increase, if you've finished with the glue, I'll pass it down here. You can grab some glue. And that layering up of paper actually makes that section of the mechanism rigid enough. You know, it doesn't make it completely rigid, but it makes it rigid enough. And that's the similar principle to the fold printing. So you can use, this kit here uses two types of material. One is a craft paper and the other is a Japanese architectural washi paper. So it's basically not the super expensive washi paper that's made by hand and costs $25 a sheet. It comes on rolls, and if you need to repair your shoji at home in your apartment in Japan, that's what you do. You buy the rolls that I use for this. I apologise, the video is pretty quick. And so the nice thing about video instruction is you can pause it, right? So this is the great part of it. You can pause it and stop it. And so all of the video instruction for the Oribokit, all of the instruction is video based. So that's it. So this particular mechanism has been patented for surgical purposes. So it's a microsurgical device. So the thing about that is you want them to be very small. So as they're inserting them into your body through a catheter of some sort, this little tiny mechanism can go inside and can be used very dexterously. And that's something you notice with the bots, is that they have this expansion and contraction that you can use quite beautifully. It's in the next video, which I'll show so you can see. So that's about the range of movement that you can get from that. But from the actual, once you hook it up to a mechanism, it actually opens out completely wide.
Being structure.
Yeah, it's very much a beautiful mechanism.
Are there certain angles that pop up all the time in these things?
I did a study of this one to see what angles or how long, because you can, of course, you can adjust it, or you can make it longer, or you can make it fatter or wider. I found for one of the angles 110 degrees was pretty optimal, but that's not a very common origami angle. In classic origami, you find 45 degrees, 90 degrees, 22.5 degrees keep occurring, just divisions of a square. The other angles that pop up all the time, their kind of more recent addition is 60 degrees, 30 degrees, 15 degrees.
Right.
So I've got a friend, Jun Mayakawa, designed a penguin, and he called it the minus 15 degree penguin. Right. You know, and it's a penguin that's got a lot of 15 degree angles in it. So he's a very, very beautiful style. So I think that part might be clear. I'll just skip into this one. I'll just see if this is, yeah, I think this might be the full thing. Okay, so this is the part where it sort of starts to come. This part's not included in this instance, but basically what we do is we glue the rigid circuit board connectors on, put some connectors onto the piece, thread up the control wire. So that control wire connects to the servo, so the little motor that moves backwards and forwards, and you can see the range of movement that suddenly appears out of the mechanism. So not what you can get a lot more out of it, but you have to be able to pull and push that centre plate. So it's really, really beautiful. I'll just show you that again.
Is it a little motor, or are you using magnets?
No, it's a little motor.
Okay.
So this one, yeah, these ones here, just little tiny mini servo motors.
Right, okay.
Yeah, and they've got a little arm on them.
Yeah.
That turns backwards and forwards, and so what that does is it pulls the wire backwards and forwards through the cable. So you can come up and have a look and see this one if you like. This one just moves gradually backwards and forwards. I'll just set it to low.
Yeah, that was pretty when they were opening and closing.
Yeah. I'll just set the low and high. Oh, I must have bumped it. Yeah, and so this mechanism just moves backwards and forwards. I think I inadvertently rebooted it. Let's wait.
That one's forwards, isn't it?
Yeah, so that one's forward, so I might just turn it off. And so what you can do is you can open and close. Yeah, so you can. That's the mechanism that happens. So as it moves forwards and backwards, so this is connected up into there, fits into there, and that. So it's the same idea, just moving two parallel plates apart is causing this expansion and contraction. So you could do it with other mechanical structures. So you could take the Ori, or in this case with the Kresling pattern here, it has a fixed plate here, and this is the moving plate here, and so you can extend it and contract it like this. Part of my research at the moment looks at, can I do this with air or fluids, so use pneumatics to do this. The hard part is making it stay together once you apply pressure. And the difficulty of fabricating a waterproof, airtight, is still an open question for me. I've been looking at different techniques. I'd love to have access to, kind of being able to do rotational moulding silicon and things like that. I've tried lots of various things. It's a really, really interesting problem.
Using like hydraulic fluid.
Yeah, to expand it and contract it. Yeah, which would be very, very interesting. But for practical purposes, for making artworks, for making things that are easy to change and set up, it's like if I want to have this as a pneumatic artwork just using air, I need an air compressor, I need a pneumatic controller, and I need all these things. And suddenly the physical weight of carrying this work somewhere, whereas this fits in a cardboard box and it's very, very simple and light. And so I actually prefer this technique for doing prototyping of these mechanisms. Yeah. So yeah, it's kind of it's taken just 20 years or so to get from the idea of Oribot to here. But the idea for this kit is that you get the advantage of starting 20 years down the track, everything's prepared, and you can start prototyping and building mechanisms with this kit. Yeah. And I think that's it. Thank you. If you've got questions, I've got kits for sale if you want to buy one. There's a special price tonight. But the main thing I wanted to do tonight is just talk about the kit, introduce it, get you interested in the idea of working with it. We are doing, I'm just working on a curriculum with Explo in Boston. They've just asked me to write their origami engineering curriculum for their summer workshops. So it's very exciting. So yeah, the kit forms the main part of the curriculum. So all the experimentation happens. You've been given like the 30-second version of the expanded series of lectures. They're going to get the theory and the practicality of working with the different folding patterns and then working with the kit itself. Yeah. So
Coding and building.
there's so much.
Skill stack.
Yeah, there's a massive skill stack. But the great thing is you can start all of it's working out of once you've assembled it. It's all the circuit boards pre-assembled. You don't have to do any soldering. All you have to do is plug everything in. You get a few screws to put on to connect some things up, and there's already code running on it. So as soon as you plug it in, it'll start responding and start working. Yeah, which is a lot of work saved for you. Yeah.
What's your thesis?
It's called Ori** on the aesthetics of folding and technology. If you look up I should have had my website links on this last slide. Yeah, I think it's on the first slide actually. Oribokit, MatthewGardiner.net, you can find a link to the thesis. You can download it, read it. Just click on it, because then I get these read statistics on my research guide. It makes me look better. Yeah, I just click on it and download it and go. There's some nice pictures in it. Okay, yeah, it's an artistic thesis. So it's yeah.
3D moving.
Yeah.
So what would you say about age levels for this? I mean, obviously the 3D printers and things are more secondary reading.
Yeah.
I'm a primary teacher.
Okay.
So I'm looking at doing origami, but origami robotics really excites me.
I can understand why. So next Friday in Singleton, I'm working with a class of grade 6 kids.
Okay.
So I'd be very interested to find out how well they go.
Depends how much experience they've had on robotics too, I suppose.
Yeah, it's mostly for the assembly of the kit. It comes down to sort of fine motor skills, patience.
Yeah.
There's super glue involved in the assembly of some parts, but it's possible to use other glues.
Yeah.
I prefer super glue just because it's done, instant. You know, it's all there. It is a bit dangerous at schools. I have seen some funny things in workshops, like yeah. But actually, you can do most of the assembly with a little bit more drying time. So just with PVA or something like that. So I like super glue for the. It adds a little bit of rigidity because it makes it. It's a bit like putting resin into fiberglass. It sort of makes it stiff. But it doesn't need it. But and it's also instant because you got to hold it in place while it's gluing. So it's super glue safety is probably the first part of the lesson. And so the kit is, due to Australian safety regulations, is marketed at 14 plus because it's only 5 volts going through it from a USB connector, but it has to be safe. For lower than that, it has to be safe if someone starts putting a knife on it or something like that, and it's got 240 volts going through it. So it would be tested with that, and so it would have failed that test. But if I put 14 plus, it can be sold. So yes, so it's 14 plus and suggested adult supervision. Yeah, but it's the same for all Arduino things. Like any Arduino you buy is exactly the same. Yeah.
So how did you get away with having a grade 6 do it?
Because they'll be supervised.
Yeah.
So yeah, and so most of the workshop is based around building the blossoms,
Yes.
which are going into a public art installation.
Yep.
And so everything that we do in terms of interacting with or plugging things in will happen unpowered, and once it's powered, we'll make sure that's and it's a small group. So yeah, so it's feeling very comfortable with that. But yeah, for high school students, especially later high school students, yeah, if they start getting given ideas for how they can adjust, like take folding patterns, how they can take folding patterns and use like a laser cutter to cut them and then fold them. If they can use just even a vinyl plotter, which just has a knife just to do perforations or cut things out. All of those things, like just simple 2D design, you can then jump into fabricating them, and using the right materials, a bit of 3D printing to make some plates. You could, invent your own Oribot, in a very short amount of time. And that's what I'm interested in finding out. Yeah.
That recent group in America that did the workshop, and then they extended it, so you had some great photos of what the students then did based on learning this. Then they took it a step further and did their own, like what could they do next?
Yeah, they had like a 3 or 4 week unit for this one class. And I think it's Professor Winkler took it in Indiana, and the idea was to give them the kit and let them make their own creative project. So the class unit was called Art and Robotics, and there's artistic projects that use robotics, but there's not many kits that give you the basic elements that you need to use. I mean, the main thing that the kit has is you can just put a servo motor straight on there and plug it in. And it's already mounted, it's already fixed. It comes with the cables and the wire, so everything, all those things are just fit together and they work. So there's actually, I think I spent most of lockdown building and designing and perfecting all of the components. And it's gone through quite a number of iterations. But that group in Indiana did some, like one guy did a thing where it kind of was like really took it a different direction, made a mechanism so it kind of with grabbing the ground and moving itself forward. There was quite a few variations. I haven't got them at hand to show you. Yeah.
And so you can program its speed and its rhythm, can you?
Yeah, you can.
Servo speeds and when they come on and go off, or
that's exactly.
go in both directions.
Yeah, they can go in both directions. You can control the speed at which they move from one place to another. What this one does is it has a little light sensor on here that as it detects less light, it moves one direction. As it detects more light, it goes in the other direction. It also has an autonomous mode. If it doesn't detect much light change, it just does a little movement periodically. But yes, you can program all of those things. Once you get into the Arduino level, then you can start like controlling it to do different things or respond in different ways. Add another sensor to it. There's little soldering pins on the side that you can add another sensor to, which is all good. Yeah, it's a lot of fun. Yeah.
There are some fields that we're getting into, so soft robotics, using flexible materials and for sort of almost dexterity type things. So I can see the origami is a big influence.
Yeah, it has. There's a group did a project called elastomeric origami at the Weiss Institute at Harvard, And they did probably about 10 years ago now. They've done quite a lot of work in that, like a lot of gripper, and there's also related work at MIT that they've produced soft robotic grippers. I think, you found one that was a group that were doing marine research.
To clean and treat coral. So they were trying to work on the right mechanisms so they could be gentle enough not to destroy the coral, but strong enough that they could scrape it clean.
Okay, wonderful.
Yeah, and so that's one of the sort of, this work is a precursor to, making those. The reason I invested so much time in sort of not only aesthetically developing this technique was that I figured I could eventually get to the point where I could just print the robotic geometry that I wanted. And if the material has all the right properties, like it's waterproof or whatever, then I'm at a new advantage. And yeah, I'm now at a slightly different point, which I can't share just yet, but it's actually adds in sensing and so forth directly into the materials. We did some work last year with Oribotic Instruments. So looking at a musical interface that's folded. So it has conductive and materials in it, so it can do touch sensing. The other thing we're looking at is detecting the angle between plates, so it could be a performative tool. It's really, so we look at doing things like angle sensing, fold angle sensing, but we're trying to sense an angle of a millimetre fold using only material properties. So, resistive or capacitive change in a material. Yeah. I was actually talking to some guys at which department are they in? They do a lot of work with thread spinning. Yeah, those guys. They were telling me some materials that I'm going to try out. Highly conductive polymers. P.dot PSS.
Another group that came out of there, intelligent materials. They're doing a lot with mats and things. So they started doing a COVID one where it sort of showed you on the map where you were sort of 1.5 metres away. And then elderly residential care, if someone had fallen down, detected there was a pressure there for too long, and so they wanted to learn something. So I think the sensing and electronics into materials.
It's pretty big at the moment. Yeah. There's a lot of new materials and a lot of new techniques that have emerged, and so our research aims to integrate that into artistic results. So the instruments are kind of performative, but we think it has other applications, like as you've just described. Yeah.
This is on YouTube of the instruments in their most embryonic stage.
Oh yeah. There's a YouTube clip on the Ars Electronica website. I've yet to post it on mine. I'll probably do that tonight. Yeah. So you can watch.
So the performance done with them. So musicians come and they're sort of playing an orchestra. So the piece all together, with the
super experimental. Yeah. It's great stuff.
Even with primary schools, you can show them those sorts of clips and say, this is where this is heading, but you are learning just the basics of this.
I think this is the thing I really like about it, is it's, and I had the experience once of, had a show in Tokyo, and I had a translator to help me talk to a visitor. And they were looking at little examples that I had of folded patterns, and they were there to hold and to move, so you could have this tactile experience of thinking. And while he was playing with them, he went, "Oh, I've seen this type of thing somewhere else in the city," and could immediately start imagining what could happen with it. And that's the other great thing about teaching with folding, is you've got the tactility to work with, and you've got materials that you're holding. As you start doing these base patterns, you start getting ideas and concepts come to your mind about different things that it could be used for, and that's a very different way of thinking and learning. The actual intelligence happens somewhere between your hands and the object and the ideas that it conjures up, and that's what I really enjoy about this particular quality of teaching and of experience. Yeah, that's why I'm still doing it. Yeah. Yeah. All right. So yes, as I said, if you would like to buy a kit, they're over here. There's a little price list. You can consider it. I've got T-shirts. This is my one moment I'm being a salesperson. Yeah, the kits are these ones. So they're a base kit which comes with one flower, and there's a deluxe kit which comes with all 3 flowers. All right, so that's the difference. And I think we've got the. Oh yeah. 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 Just waiting for it.
There you go. See? So it's the
And the original programming has them moving at doing the same thing but slightly delayed from each other. Yeah. And they're also available on the website, so you don't have to, yeah. But there is a special price tonight. And you save on postage.
Have you spoken to VCA?
No, I'm an alumni from there, but yeah.
Get back there.
Yeah, I probably should, yeah.
Last time I went to the student exhibition, they had a few motors doing some really dumb things.
Yeah, yeah.
Just moving things back and forth.
Hmm.